Right. Thank you, Madam MC, for the privilege. So, as you rightly heard, we are going to see how we can use some statistical packages in running normality tests. Just to see, we want to know how normally distributed our data set we have are, and specifically continuous variables. So we'll be using a number of statistical packages ranging from STATA as well as Python. Right, so if you join our discussion from yesterday, you'll come to see that we imported a data which we called the Framingham Heart Study, which we used in our demonstration of descriptive statistics. So today we want to focus on the normality test. And if you listen carefully to the previous video, there were a number of tests that were mentioned. The Shapiro-Wilk normality test was mentioned. Mogorov-Smirnov was also mentioned. Pearson-Omnibus normality test was also mentioned. But we will demonstrate just the Shapiro-Wilk normality with both the STATA and then the Python platform. So the code that we need to type to be able to have our Shapiro-Wilk normality test displayed with the STATA platform is simply S-Wilk. I think earlier on I ran this test. So it's just S-Wilk, and then you type the variable you're interested in. So when we look here, we have different variables here. So let's select a different than BMI. So let's select CV, and then we click on enter. Right, so it gives us a display of the results. So it's just so simple by just typing S-Quick CVD, which is the variable name over here. Just sorry, SPSS. Hey, sorry, I'm used to just an SPSS. So STATA simply calculates this value for you in a few seconds. So here we have the probability value here, and we also have the Z-score. So if we are saying that our level of confidence for the normality hypothesis test is 95%, we are confident we'll be right at 95%. Our Z-score for 95 is 1.96. So where we have a Z-score calculated being less than the standard 1.96, then we can fail to reject that this data is normally distributed. Now, if we have it greater than it, then we have to reject it. So similarly, when we come to the p-value, the p-value here, that's the probability value. A value which is less than 0.05 will mean that our data set is significantly different from a normally distributed data. So we have to reject the null hypothesis. But if it is greater than it, then it means that it is not statistically different. So we fail to reject the null hypothesis. So in this case, we have the p-value being greater than 0.05. So it means that we can say our data set here is normally distributed. And similarly here too, our Z-score is lower than 1.96. So we can also base our conclusion that this data set is normally distributed. Now let's run the same for Francia, BMI. Good. So here we realize the conclusions that we can draw from both normality tests are the same. This one, the p-value is greater than 0.5, 0.05. And so we would say this data set is normally distributed. So we fail to reject the null hypothesis, which says that our data set is normally distributed. And here too is greater than 1 point, is less than 1.96. And so we will also make that same conclusion. And similar conclusion is drawn with this variable. So it's not always a situation where you have contradiction between these two normality tests, but situations where you have this kind of contradiction, you may want to explore other avenues like the visual inspection. You can use a histogram and all that to be able to explore that. So basically, this is it for the Shapiro week. So let's draw. Lastly, let's draw the QQ plot for EMI, and then see how it looks like, and compare it to what we had for the CV. So as you can see here, this is quite normally distributed. Why are we saying that? Because the data points are lying close to the 45-degree line over here. So when they are close to it in this distribution, in this distributed fashion, then we can see that our data set is normally distributed. But as we saw in the earlier one, it was looking like 2 points, 2 major points, which means that our data set is not normally distributed. So basically, this is it for the STATA platform. So I'm moving now to the, yes, I'm moving